So friends, welcome back. As we were discussing about the classification of the alkaloids, and we already discussed few classes of the alkaloids that have been classified on the basis of the type of hydrocyclic ring. So in continuation with the previous lecture, the next class of the alkaloids is indole alkaloids, and these are those alkaloids which are having the indole nucleus in their structure, and perhaps these alkaloids form the largest group of alkaloids because more than 4,000 indole alkaloids have been identified and isolated from the nature, and these indole alkaloids are derived from the amino acid tryptophan, and they are broadly categorized into non-isoprenoid indole alkaloids and isoprenoid or terpenoidal indole alkaloids. It has been observed that many times there is an isoprene unit that gets attached to the indole nucleus, and that is why the classification of indole alkaloid is based upon the isoprenoid or the non-isoprenoid alkaloids. So coming on to the non-isoprenoid indole alkaloids, these are further categorized into three major categories, that is simple indole alkaloids, carbolin alkaloids and pyrroloindole alkaloids, and this classification is again on the basis of the variation in their chemical structure. The common examples of simple indole alkaloid is 5-hydroxytryptamine, that is 5-HT, or commonly known as serotonin, and psilocybin. Now serotonin, we all know that is an important neurotransmitter responsible for the sleep functions, whereas psilocybin is a very toxic simple indole alkaloid that has been obtained from the mushrooms belonging to psilocybe genus. Coming on to the carbolin alkaloids, the common examples are hermalin and hermarin, and pyrroloindole alkaloids, they have a pyrrolidine ring in their nucleus, and the common example is physostigmine, that is obtained from the Physostigma venenosum. And you can clearly see in the structure of physostigmine the presence of a pyrrolidine ring along with the indole nucleus. Now hermalin and physostigmine are well known acetylcholinesterase inhibitors, and again I move on to acetylcholine, which is an important neurotransmitter for memory functions. Now under pathological conditions, the level of acetylcholine decreases in the brain, which causes impairment of memory. Now acetylcholine basically gets degraded by an enzyme acetylcholinesterase, and since hermalin and physostigmine are the alkaloids which inhibit the acetylcholinesterase enzyme, and by inhibiting this particular enzyme they help in maintaining the levels of acetylcholine, and this is the reason why physostigmine was approved by US FDA for the symptomatic treatment of the patients that are suffering from memory impairment or Alzheimer's disease, because this alkaloid basically inhibits that particular enzyme and help in maintaining the acetylcholine levels in the brain, which help in maintaining the memory functions, though the effects are symptomatic only. They do not alter the development or occurrence of the disease. Now coming on to the isoprenoid or the terpenoidal indole alkaloids, and these are again divided on the basis of number of isoprene units that are attached to the indole nucleus, and on those basis these are further categorized into hemiterpenoid and monoterpenoid indole alkaloids. Hemiterpenoid, in which only one isoprene unit is attached to the indole nucleus, and the common examples are the alkaloids obtained from the fungus Claviceps purpurea, that is ergot, and the alkaloids are ergotamine, ergometrine. And coming on to the monoterpenoid indole alkaloids, these indole alkaloids are further categorized on the basis of the number of carbon chain length, and if the carbon chain length in the isoprene unit is of 9 carbons, then they form C9 monoterpenoid indole alkaloids, and the various examples of these alkaloids are ajmalin, strychnine and brucine. And ajmalin, we know we find this alkaloid in the roots and rhizomes of Rauwolfia serpentina, and strychnine and brucine are found in the seeds of Strychnos nux vomica. Then the further subdivision is of C10 monoterpenoid indole alkaloids, means here the 10 carbon chain length side chain is attached to the indole nucleus, and the common examples are reserpine, ajmelicine, yohimbine and catharanthine. The first three alkaloids are normally found in the roots and rhizomes of Rauwolfia serpentina, and catharanthine is an alkaloid that is found in Vinca rosea. Now, apart from these C9 or monoterpenoid or hemiterpenoidal indole alkaloids, indole alkaloids also occur as dimer alkaloids, that is, two single indole alkaloids units, they basically join together to form the main alkaloid, and that is since two single units get attached, they are known as dimeric alkaloids. And the common examples of dimeric alkaloids are vincristine and vinblastine, and we know that these are well known anti-cancer alkaloids and are found in Vinca rosea, that is Catharanthus roseus. And in this slide you can see the structures of the different indole alkaloids. The first one, that is hemiterpenoid, shows the structures of ergot alkaloids, and below is the picture of the fungus that grows on the rye plant. The black outgrowths, they are nothing but the fungal outgrowths, that is the ergot outgrowths. Second, we have C9 alkaloids, strychnine and ajmelin. Strychnine is obtained from the seeds of Strychnos nux vomica, and the seeds, the picture of the seeds you can see, that is the third picture, and in the middle we are having the picture of Rauwolfia serpentina, from which we get ajmelin, ajmelicine. So these are the structures of the various types of isoprenoid or the terpenoidal indole alkaloids. The next class is of quinazoline alkaloids, and these are the alkaloids which are having quinazoline structure or the nucleus in their structure, and these alkaloids are found in the plants that belong to families of Acanthaceae, Rutaceae, Saxifragaceae, and also from the microorganism. In certain kind of bacteria they are found. Around 70 quinazoline alkaloids have been isolated and identified from the nature, and these are further categorized into simple quinazoline alkaloids and pyroquinazoline alkaloids. Now, arborin is a common example of a simple quinazoline alkaloid, and it is obtained from Glucosmus arborea, whereas vasicine is a common example of pyrroloquinazoline alkaloid, and vasicine is an alkaloid that has been isolated from the plant Erythoda vasaca. Now, vasaca is commonly used for its cough suppressant and expectorant action, and there is a herbal formulation by the name of Vasaca Madhu in the market, and it contains the alkaloid vasicine, and since it is also having a partial pyrrolidine structure ring in its structure, that's why it belongs to pyrroloquinazoline category. Next we have norlupinane or quinolizidine alkaloids, and these alkaloids have norlupine nucleus in their structure, and these alkaloids are found mainly in the members of Fabaceae family, and more than 200 alkaloids have been identified in the nature. And on the basis of the structure, these are further categorized into 6 different categories, and the common examples are lupinin and sparatinin, and the third type is matrin. Now, as you can clearly see, the variation in the structural molecules of these alkaloids, lupinin and sparatin, are isolated from the species of genus Lupinus, and matrin is an alkaloid that has been isolated from the genus of from the members of the genus Sophora. So, likewise, on the basis of the structure, 3 other categories are also there, but these are the 3 major subclasses of the norlupinane type of alkaloids. Next is the purine alkaloids, and since these alkaloids, as we have already discussed in Hegnoir classification also, these alkaloids are not derived from amino acids, but they have nitrogen atom in their heterocyclic ring, and therefore these are also known as pseudo alkaloids. And purine alkaloid is basically obtained by the fusion of pyrimidine and imidazole alkaloid and they give rise to a purine nucleus. And these alkaloids are amphoteric in nature, and as they are soluble in both water and organic solvents. And the common examples belonging to the purine alkaloid category are caffeine, theophylline, which we obtain from tea and coffee, and they are largely used as CNS stimulants. Next we have is the steroidal alkaloids, and these are the alkaloids which have a steroidal nucleus, cyclopentanophenanthrene ring nucleus in their structure, and depending upon the number of the carbon atoms present in the structure, they are further categorized into C21, C24 and C27 steroidal alkaloids. C21 and C24 steroidal alkaloids are limited in nature and they have a very limited distribution, whereas the steroidal alkaloids having 24 carbon atoms, they are specific to the members of the family Buccaceae, and the alkaloids having 27 carbon atoms, they are found in the members of family Solanaceae and Liliaceae. And the common examples of these categories are conicine and solasodine. And solasodine, we know that it is obtained from different species or belonging to Solanaceae family, and conicine we obtain from Curchi. Now, apart from these 21, 24 and C27 steroidal alkaloids, there are also examples of 32 carbon chain steroidal alkaloids in nature, and the common examples are veratrudine, which is isolated from different species of veratrum. So, the next category is of terpenoidal alkaloids, and these terpenoidal alkaloids may have terpenoidal structure, or they are derived from the isoprene units, and many a times since they are not derived from the amino acids, but still they have nitrogen atom in their heterocyclic ring, they are also considered as pseudo alkaloids. And the most common examples are aconitine, which is derived from the aconitum species belonging to family Ranunculaceae, and you can clearly see the complex structure of aconitine. So, this was about the classification of the alkaloids that was largely based on the type of the heterocyclic ring, and till now we have clearly see that how there is large variation in the chemical structure of the alkaloids, and it's nearly impossible to categorize or to bring all these alkaloids under one umbrella, and therefore the major difficulty is that they do not belong to a homogeneous group, and that is why it's very difficult to define alkaloids with a single definition. Now, coming on to the third type of classification of alkaloids, and this is on the basis of their molecular precursor, or the compounds or the agents from which they are synthesized biosynthetically. And since we know that amino acids are normally derived from alkaloids are normally derived from amino acids, so these are classified on the basis of the amino acid from which they are synthesized. And as you can see in the table, the alkaloids that are derived from tyrosine amino acid, they are further categorized into phenylethylamines, benzyl isoquinolines, phenyl ethyl isoquinolines, and tetrahydroisoquinolines, and we have already discussed the examples of the alkaloid under these categories, like ephedrine, mescaline under phenylethylamine, morphine, codeine under benzyl isoquinoline, then galanthamine and colchicine under phenylethyl isoquinoline or tropyloin alkaloids, then ametin and cephalin under tetrahydroisoquinoline. Similarly, the alkaloids that are derived from ornithine, they are categorized into tropane, pyrrolidine and pyrrolizidine alkaloids, and the common examples are atropine, hyoscyamus of tropane alkaloids. Pyrrolidine alkaloids have examples of hygrine and cuscohygrine, symphetin and metrolidine, they belong to pyrrolizidine alkaloids. Next we have the alkaloids that are derived from tryptophan, and two types of alkaloid, two categories of alkaloids are derived from tryptophan, that is indole and quinoline. And we have already discussed the examples of indole alkaloids such as ajmalicine, strychnine, catharanthine, reserpine, vincristine. Vincristine, obviously, vincristine is a dimeric indole alkaloid, then ergotamine. And under quinoline alkaloids, we have quinine, quinidine, cinchonine, and cinchonidine. Then the other alkaloids such as piperidine, quinozolidine, and indolizidine, these are the alkaloids that are derived from the amino acid lysine, and the examples such as piperin and enaferin, they belong to piperidine class. Then lupin and spartin, they belong to quinozolidine class. Then schwanzonine, they basically belong to indolizidine class. And the last is histidine, and the alkaloids belonging to imidazole class, they are derived from histidine, and the common examples of imidazole alkaloids are pilocarpine and pilocin. So this was the third method of or the way of classification of alkaloids, that was largely based upon their molecular precursor. Now coming on to the next part of the alkaloids, that is the extraction of alkaloids. Now, as we have discussed in the previous lecture, that in plants or in nature, alkaloids occur in two forms, that is in the form of free bases or in the form of salts. And we all know that bases are soluble in organic solvent and salts are soluble in water. Obviously, exceptions are there in both the cases, but by and large we consider that free basic alkaloids or the free bases of the alkaloids, they are more soluble in organic solvent, and their salt forms are more soluble in water. Now, since both these forms are present in the plant matrix, so there can be two broad approaches of extraction of alkaloids, and these two broad approaches, they basically utilize the differential solubility of the alkaloids. Now, either we can convert all the free base alkaloids into the salt form, or we can convert all the salt form alkaloids present in the plant matrix into the base form. And how to do it? We take the required amount of the powdered plant material, that is the plant matrix. Then if we want to convert the salt form alkaloids present in the matrix into the free bases, we will mix the plant material or the powdered plant material with a weak base, either 10% or 20% lime weight by weight, or we can treat the powdered material with dilute ammonium hydroxide or ammonia. Now, when you mix it with lime, we have to moisten the mixture with water. Water will imbibe into the plant matrix, taking along with it the alkali, that is the lime. And when the lime or the alkali molecules enter into the plant matrix, they will react with the alkaloids that are present in the salt form and liberate the alkaloids from their salt form. And as we discussed this property of the alkaloids, that whenever they are treated with weak alkalis, they liberate the salt alkaloids. So once the alkaloids are liberated from their salt form, we kept that mixture of the base and the powdered plant material, which is moistened with water, overnight, so that all the alkaloids that are present in the salt form, they get converted into the free base alkaloid form. So after 24 hours, we completely dry the mixture, and now this mixture will contain alkaloids mainly in the free base form, and then we know that the alkaloids that are present in free base form are soluble in organic solvent, and then we can extract that plant material with an organic solvent such as chloroform or dichloromethane. Now, once extraction is complete, we get an organic solvent. We will dry this, evaporate the organic solvent under vacuum or reduced pressure, and we will get a residue. Now, this residue, since it is being extracted with the help of organic solvent, it will largely contains the alkaloids that are present in free base form. Now, along with the alkaloids, there will be so many other constituents that were soluble in organic solvent. So now what we will do is we will treat this dry residue with a dilute acid or 2 normal HCl, say for example. When you will treat this residue with a dilute acid, it will convert all the alkaloids again into salt form, and the alkaloids which get converted into the salt form, they will shift into the aqueous or the dilute acidic layer, leaving behind the impurities or the other constituents that were soluble in the organic solvent, but now they are insoluble in the aqueous region. Now from here we will filter this mixture, and the filtrate which we will get will be the dilute acidic filtrate, which will be having all the alkaloids in the salt form that we extracted from the organic residue. Now we will again basify this this acidic extract, and when we will basify this acidic extract, it will again convert the alkaloids that are present in the salt form into free bases, leaving behind the impurities that were slightly soluble in the aqueous region and come along while extracting the alkaloid from the organic residue. Now when the alkaloids they get converted into free bases, they will become slightly insoluble in the aqueous medium, because free alkaloidal bases are more soluble in organic solvent, and this acidic solution or the extract will become slightly turbid. Now we can again partition this acidic extract with an organic solvent, say chloroform again or dichloromethane, depending upon the solubility of the alkaloid. And what will happen now is the alkaloids which have been converted into free base form by addition of alkali in the acidic extract, now they will shift to the organic layer, and from there we can separate the organic layer in a separating funnel, and it can be dried, or the alkaloids can be crystallized from that particular organic layer. So this was one approach by which we are converting all the alkaloids that are present in in the base form and the salt form into free alkaloidal bases by treating the plant material with alkali and then extracting with organic solvent, and then a step of acidification and basification to further purify the alkaloids, and then we crystallize the alkaloid from the organic layer. Now the second approach is exactly opposite of this one. Here in the second approach we can convert all the alkaloids into the salt form by treating or extracting the plant material with an acidic solvent, either acidic methanol, either acidic ethanol, and acidic methanol or ethanol can be prepared by adding tartaric acid or very dilute HCl to the solvents, and then when we extract the plant mixture with the acidic solvent, so all the alkaloids will get converted into salt form and will be extracted from the plant material. Now once the alkaloids are extracted from the plant material, we filter the extract or filter the extract, then we take the filtrate and then we again basify the filtrate with dilute ammonia or any suitable dilute base. Now when we basify this acidic extract, again the alkaloids which are present in the salt form, they will get converted into free basic form, and from there we can separate the alkaloids by extracting the basic extract with the suitable organic solvent. So these are the two broad approaches by which we can extract the alkaloids. Apart from these two broad approaches, there are certain specific methods for the alkaloids, such as TAS-Otto method, in which the drug is being extracted with ethanol, which has already been acidified with tartaric acid. And so this is the second, this extraction method is based on the second approach, where we are converting alkaloids into the salt form. Now we will filter this alcoholic extract and alcohol is distilled off, and this alcoholic extract is then further treated with petroleum ether to remove all kind of pigments or coloring matter or fatty material from the extract, and then we separate the petroleum ether layer, which is discarded, and the remaining alcoholic extract is again further extracted with alcohol. Now initially we discussed under the properties that both salt form and base form of alkaloids are soluble in alcohol, and therefore the remaining aqueous extract in Stas-Otto method is again extracted with alcohol to get an alcoholic extract which is rich in alkaloids. Now from this complex mixture or the alkaloid rich mixture, alkaloids can further be separated or purified either by a acidification and basification step, or they can further be purified by using various chromatographic techniques like thin layer chromatography or HPLC or any preparative chromatographic method. So this was Stas-Otto method, which was largely based on the second category of the extraction method. Similarly, there is another extraction method which is known by the name of Kippenberger method. In this, the plant material is basically first treated with tannin glycerol solution. Now, tannin glycerol solution basically will help in precipitating certain proteinaceous compounds which may interfere in the extraction of the alkaloids, because we know that whenever tannin reacts with protein, it causes precipitation of the protein. So that's why if any proteinaceous material is present in the plant, then it will get precipitated by treatment with tannin glycerol solution. After the treatment, the mixture is filtered, and the filtrate is again treated with petroleum ether. Now, the usage of petroleum ether is largely to remove the pigments or the coloring matter or the fatty material from that extract, and once it is done, the petroleum ether layer is discarded and the remaining extract is again acidified with a dilute acid, thereby converting all the acids into the salt form, and then it is again basified. Now, when it is converted into salt form, all the alkaloids they will get into solubilized form, but certain impurities that will be less soluble in the aqueous region, they will start getting precipitated, and we can further filter this extract. So now we get an acidified extract which is having all the alkaloids in the salt form. The second step will be again the basification, where we basify this acidified extract with the help of dilute ammonia or ammonium hydroxide, and when we basify this extract, we are converting all the alkaloids that are present in the salt form again to the free base form, and then we extract this basified mixture with the help of an organic solvent, either chloroform or dichloromethane. So all the alkaloids will now come into the organic layer by virtue of their more solubility in the organic solvent, and from this organic solvent we can separate the alkaloids, we can crystallize them, or we can again purify these alkaloids with the help of different chromatographic techniques. Now these were the approaches of extraction of alkaloids, but the methods that are used for extraction, they are uniform in all these approaches. We can go for maceration, we can go for percolation, we can go for soxalate extraction, we can go for reflux extraction. These are the conventional extraction techniques. We can also use modern extraction techniques such as supercritical fluid extraction, microwave assisted extraction, ultrasonic wave assisted extraction, and so on and so forth. So this was basically about the different methods by which you can extract the alkaloids. Now coming on to their detection of presence or absence of alkaloid in a given plant material, and this can be done with the help of different chemical tests. These are the four common or broadly or widely used chemical tests for detecting the presence or absence of alkaloids. And first one is Mayer's test, which is done with the help of Mayer's reagent, which is nothing but potassium mercuric iodide solution. And whenever the acidified plant extract is treated with Mayer's reagent, you get a creamish precipitate. Similarly, other tests are Dragendorf test, Wagner's test, and Hager's test. In Dragendorf test, we get orangish red precipitates or brick red precipitates. Then in Wagner's test, we get brownish reddish precipitates, and in Hager's test, we get yellowish precipitates. And if we get all these precipitates, that indicate the presence of alkaloid in a given plant mixture or plant material. Now, apart from these common or broad chemical tests, there are certain specific chemical tests also, such as Vitale-Morin's test, and these specific tests are for specific alkaloids, as Vitale-Morin test is specifically for tropane alkaloids like atropine, hyoscyamine or hyoscine, and you get a violet color as an end point of this test. Then we have Mirexide test, which is largely used to detect the presence of caffeine, and you get pinkish or reddish color precipitates or color in as an endpoint of the test. Then Van Ark test is there, in which we get blue colored endpoint, and it is largely used for ergot alkaloid. Likewise, Rosequin test is there, which is largely used to detect the presence of quinine in the given extract. Now, many a times we get a false positive test or a false negative test while performing these general chemical tests like Mayer's, Dragendorf, Wagner's or Hager's. Now, the conditions where we get a false positive test is because, as I told you, that plant material may contain certain proteinaceous or tannin compounds which may also react with the heavy metals that are present in these reagents, that is Mayer's, Dragendorf, Wagner's or Hager's. And if the plant material is having such proteinaceous or tannin compounds which can form complex with these with the heavy metals heavy metals present in these reagents, we can get a false positive test, because in such cases you will get precipitates irrespective whether the alkaloid is present in the plant or not. So, to overcome such false positive test, the best way is to go for a series of acidification and basification of the extract, thereby removing all those interfering compounds such as tannins or protein from the extract, and then we perform these Mayer test, Dragendorf's or Wagner's or Hager's test, and if we get precipitates in the final step, that gives the confirmation, yes, that alkaloids are present in the particular plant material. And in case of false negative conditions, the false negative tests are obtained in case of quaternary alkaloids, where these alkaloids are more soluble in the aqueous media, and normally we discard the aqueous media, and if we don't test the aqueous media also, we may get a false negative indication that the alkaloids are absent in the plant material, though they were present but in the form of quaternary alkaloids. So, this was about the chemical test of the alkaloids. Now, coming on to the uses of alkaloids. Alkaloids have variety of uses ranging from analgesic, antitussive, CNS stimulant, acetylcholinesterase inhibitory activity, anti-cancer, muscle relaxant, anti-gout, ophthalmic uses, anti-hypertensive effect, and all the alkaloids are largely used in these pharmacological activities to cure certain disorders and to give relief to the patient. So, friend, this was all about the alkaloids. We started from the brief historical background, then distribution in the nature, then we come on to the definitions of the alkaloids, then their nomenclature, their properties, then how these are classified. There are different methods of classification. Then we discussed about the extraction methods of alkaloid, how these alkaloids can be detected in the plant matrix, and the uses of alkaloids. Thank you.